Welcome to This Explainer. Today, we're ditching the stovetop splatter and completely flipping the script on breakfast. We've all been there, right? Dodging hot grease, dealing with those unevenly cooked strips where one half is completely burnt and the other half is flabby rubber. It's a universal morning struggle. But we are transforming this everyday kitchen task into a fascinating exercise in controlled lipid extraction. So throw out everything you thought you knew about cooking bacon, because we're diving into the hard, undeniable science of perfect crispness.
Here is our roadmap for today. We'll start with the science of bacon, move into Phase 1 for our pork protocol, tackle Phase 2 with the turkey variant, and wrap up by troubleshooting some common thermal defects.
All right, Part 1, the science of bacon, or more accurately, controlled lipid extraction.
To really get this right, we need a total mindset shift. We're stepping out of basic cooking and right into applied physics. The crucial point here is that we aren't just cooking meat, we are executing controlled lipid extraction. When you put bacon in the oven, your main objective isn't just applying heat to the muscle. It's carefully, methodically coaxing that solid white fat right out of the meat fibers. Why? Because rendering that fat is the exact mechanism that turns those chewy, gummy white pockets into pure, melt-in-your-mouth crunch. Grasping this single scientific concept literally rewrites how you'll approach your morning meal.
And this brings us to the rack fallacy, a massive physics mistake that's been passed down for years. People are constantly told to elevate their bacon on a wire rack so the grease strips away. But actually, scratch that. Elevating the meat means the fat abandons it immediately. The bacon is left completely exposed, roasting in hot, dry air. That harsh environment gives you a brittle, dry crunch that basically shatters into dust. Contrast that with what happens on parchment paper. The fat pools naturally around the meat. You're gently, evenly frying it in its own rendered liquids. The result? A magnificent, shattering, yet perfectly tender crispness.
By keeping the strips flat on parchment paper, it turns out we're basically stealing a trick from high-end French chefs. We're harnessing what the culinary world calls the confit effect. Think of an incredibly tender duck confit. You're using the bacon's own rendered fat to fry it perfectly. It's a brilliant, hyper-efficient use of the meat's natural composition, and honestly, a wire rack simply cannot compete with that. Moving on to Part 2, Phase I, our pork protocol, featuring the cold start.
So our absolute main target here is initiating a slow phase change of the solid fats without shocking the meat. Think about the thermal dynamics for a second. If you throw cold bacon into a blazing hot, preheated oven, the muscle fibers violently seize up way before the fat even has a chance to melt. It locks moisture exactly where we don't want it. What we really want instead is a gentle, gradual transition from solid fat to liquid lipid. To nail that perfect phase change, you need to follow these 5 exact steps. First, and this is absolutely critical, do not preheat your oven. Lay your thick-cut pork flat on the parchment. Edges touching? Totally fine. But never, ever overlap the strips. Overlapping immediately traps steam, and steam is the ultimate enemy of crispness. Pop the pan into that cold oven, crank it to 400 degrees Fahrenheit, and let it bake for 18 to 22 minutes. As the oven slowly warms up, the extraction happens flawlessly. Once that timer dings, immediately move the strips to paper towels to halt the thermal reaction. Let's pivot to Part 3, Phase 2, the turkey variant, which relies on lean meat convection.
Now, turkey bacon requires a completely different paradigm. The glaring issue here is that turkey is a highly processed, lean meat. It has almost zero structural rendering fat. If you try pulling that cold start trick we just used for pork, the water inside the turkey will just evaporate. You'll literally dehydrate the strip into dry meat leather. In the lab, we call this ruined breakfast catastrophic desiccation. To avoid that catastrophic desiccation, we deploy a brilliant lipid hack. It's based on one staggering physical property. Oil conducts heat 20 times faster than air. That is a massive difference. And we're going to use that extreme thermal conductivity to completely save our breakfast. By executing this specific 4-step protocol, the lean meat problem entirely vanishes. Notice the key differences here. First, you actually do preheat the oven this time, but to a slightly lower 375 degrees Fahrenheit, because lean meat burns way faster without a fat buffer. Next, we introduce an artificial lipid layer, just a microspray of avocado oil or a super light brush of olive oil. Thanks to that 20x conductivity rule, this oil acts as a thermal shield. It artificially fakes the confit effect from our pork protocol, rapidly frying the surface into a protective crust before the inside moisture can escape. Bake for 12 to 15 minutes and flip exactly halfway for that even golden browning.
Finally, Section 4, Troubleshooting Thermal Defects. Let's fix sugar burns and bacon curling.
Okay, if you've ever confidently pulled out a tray of expensive, thick-cut maple bacon only to find carbonized black strips of ruined meat, you've experienced the burnt sugar defect. It is the worst. This anomaly pops up mostly with maple-cured or brown sugar varieties when they get subjected to our standard pork protocol.
Looking at the thermal breakdown data, it's completely obvious why 400 degrees destroys sugared cures. Sugar caramelizes beautifully at 320 degrees. That's where you get that perfect sweet glaze. But right at the 350-degree mark, you enter the danger zone. It starts burning rapidly. By the time your oven hits 400 degrees, the sugar cure is fully carbonized, way before the thick fat even has a chance to render out. The fix is super simple. Just drop your target oven temperature to 350 degrees Fahrenheit and extend your bake time by an extra 5 to 8 minutes.
And lastly, let's talk about the dreaded U-shaped curl. It's incredibly frustrating when your bacon curls up and cooks unevenly. This structural defect usually happens if your baking sheet warps under intense heat or if the bacon slices are just too thin to hold their shape. Now, our cold start method naturally prevents about 90% of this curling by slowly relaxing the meat. But if you're chasing absolute restaurant flat perfection, there's an ultimate kitchen secret: physical weight. Just drop a second-rimmed baking sheet directly on top of the bacon strips while they bake. It completely neutralizes the curling problem, giving you flawless, uniform strips.
As we wrap up this explainer, I really want to leave you with something to chew on. We just broke down some seriously intricate thermodynamics and lipid extraction protocols for something as basic as a side of bacon. It really makes you wonder, right? If perfectly cooking bacon requires this level of precise science, what other everyday kitchen staples are we fundamentally misunderstanding just because we aren't looking at the physics? Keep questioning the process, and I'll see you next time.